Hello, everyone, and welcome back to the 2018 Hack Summit. We're joined here by Izaak Meckler, the co-founder and CTO of the Coda Protocol. And the Protocol is a brand new innovation that's funded by some of the best investors in Silicon Valley with the idea of a constant time blockchain. And Izaak will tell you all about it. He's got a great technical presentation for you. It's going to be educational for all of us to learn. Izaak, why don't you tell us a little bit more about your background, how you got into programming, how you got into blockchain, and your past career history. And then we'll launch right into the presentation.
Yeah, sure, my pleasure. So let's see. So immediately before working on Coda, I was a PhD student at UC Berkeley studying cryptography, kind of theoretical stuff like multi-party computation. If for any cryptography heads out there, and before that, before doing my PhD, I'd been working as a programmer at a trading firm and using OCaml. Which is, why I guess we use OCaml. Well, one of the reasons we use OCaml now, working on Coda. And before that, I have kind of a math and computer science background.
That's great. All right, well, we'd love to learn more, so feel free to launch your presentation and screen share away.
Okay, cool. Let me just queue up the presentation here.
And audience, if you have questions for Izaak, feel free to type them in on the bottom of the screen. We'll field the questions at the end of the presentation.
Okay, great. Thanks, Ed. Cool. So let's see. Let me get this out of the way. All right. So I'm going to be talking about Coda, which is a new cryptocurrency protocol. And you can think about it as a cryptocurrency protocol that kind of fits in your pocket. Yeah, let's just dive into it. What is Coda? Coda is a new cryptocurrency. What's kind of interesting about it is it's the first cryptocurrency with what we call a succinct blockchain. And what a succinct blockchain means is basically we're able to compress the blockchain down from what would be hundreds of gigabytes on a typical cryptocurrency protocol into the size of a few tweets. So it's a blockchain that always remains the same size, the size of a few tweets, no matter how many transactions happen. What's really nice about this is it makes the blockchain, the cryptocurrency, kind of scalable, secure, while remaining decentralized, so anyone can check. You can even check your blockchain kind of on a mobile phone, which I think is really amazing. I think it's cool anyway. And it's developed by a great team, so shout out to our team. Okay, so before diving into Coda itself, let me kind of set the stage a little bit, talk about the cryptocurrency landscape as I see it currently. So this is kind of a rough scientific diagram of cryptocurrency. How does it work? Well, okay, basically you have your transaction processors. These are miners if you're using proof of work, or stakers if you're using proof of stake, who are applying transactions to some kind of database. You have full nodes who are participants in the system that are tracking every single thing that the miners do to make sure that they're doing their job correctly, the processors. And then you have your typical end users who often, as is often the case, end up delegating trust to either processors or full nodes, not checking themselves what's going on, but just kind of trusting these other parties to do the checking for them. So this seems kind of strange. I mean, cryptocurrencies are supposed to be this kind of totally trustless thing. Everyone should be able to check. You don't have to delegate trust to a third party. That's kind of the whole idea. So the question is, why can't everyone be a full node? Seems like a reasonable question. Well, let's try and answer. So let's walk through kind of the life cycle of a full node as it's kind of played out in reality. So at the beginning of a cryptocurrency, when not too many transactions have happened, the blockchain is still very small. Being a full node is not so bad. You download maybe a few megabytes. Doesn't take too long. You can check the blockchain, and you're good to go. You're happy. But after some time goes on, the blockchain just grows and grows and grows. And suddenly, what was once a few megabyte blockchain has become gigs and gigs and gigs. And no longer becomes the sort of thing that's easy to check. Nonetheless, if you wanted to check, you'd start marching down the chain, you'd continue all the way to the end, and finally you get to the end, you can send your transaction, but well, okay, maybe by then maybe you should have done something else instead. You might not be so happy with how long it took. Okay, so that's kind of what's going on with being a full node. And why is this a problem? Well, it means many end users do no validation in practice, okay? Why? Well, we kind of saw full nodes in existing cryptocurrency protocols have enormous resource requirements, which get worse all the time. Every transaction that happens, it makes it harder and harder to verify the blockchain. The kind of end result here is it's very intensive to run a full node on a computer. You kind of need to have a dedicated computer, and it's essentially impossible to run on mobile. The resource requirements in terms of storage, bandwidth, computer are just too high. So what do end users do? Well, they end up delegating trust to third parties. So that's either full nodes. In the case of online wallets, you're trusting that the person you're working with is the wallet you're working with is checking the blockchain for you, or you're delegating trust to miners in the case of what are so-called light clients. So what we'd really like is maybe some kind of way to be convinced of the current state of the world, like how much money do I have, what transactions have I gotten, without having to see the history of that state. And kind of to drive the problem home, the sort of the root of the problem here is the verification mechanism that existing cryptocurrencies use is sort of inherently unscalable. Let's try and use a sort of a rough analogy. The way that it works is as if every time you wanted to spend $1, you had to check the entire history of how that dollar had been spent. Okay, so let's say you're thinking, oh, I have $1. I wonder if I can spend that $1. Well, okay. First, you need to know. Oh, let me remember. I got that $1 from my job as a cashier, and oh yeah, and then the person who gave me that $1, they got it because they were working at another cafe, and oh yeah, and the person at the cafe, or the person who spent the money at the cafe, they got it from their boss, from their paycheck, and the person and the boss got it from their super boss for their paycheck. And the super boss, I don't know, runs a McDonald's franchise, and they got it from there, and the customer at McDonald's got it from some other cafe, and okay, who cares? I mean, you're just trying to spend money. Why do you need to know the whole history? Very strange. But this is a world that we live in. So how do we get out of this world? Well, let's try and think about, kind of analyze the problem a little bit. Maybe we can understand what a solution might look like. Okay, so what we really want here is some way to certify that someone else had already checked the history without having to check it ourselves. So it's like you could say some kind of certificate that the current state was valid, which wasn't just the entire history. As an analogy, you can kind of imagine, like, let's say you wanted to invest in a business, but and you want to make sure they're financially solvent, but you don't want to look through their whole financial history yourself. One thing you can do is you can get like an auditor to do it for you, and then the auditor will produce like an audited financial statement. And so then all you have to do is just look at this audited financial statement without having to do the work of digging through all the finances yourself, which is a lot easier to check. Okay, so we want some kind of certificate, which is kind of like an audited financial statement, some kind of proof that indeed I did check the whole thing, and you don't have to worry about it for yourself because I checked it for you. So it turns out there's a really amazing technology called zkSNARKs, which essentially give us just that. You can think of the zkSNARK as like, it's one way to talk about it would be like an unforgeable certificate. Okay, well, as I said, it's this amazing cryptographic primitive. It's widely deployed in applications like Zcash, people might be familiar with. They're essentially some kind of certificate which proves that a computation was performed correctly. So, and let me say there are a few cool properties that they have. One is that they're super tiny, these certificates, so they're less than a kilobyte. They're very easy to check. You can check them in less than 10 milliseconds. And they're super versatile, so you can use them to certify the correctness of any computation. It doesn't just have to be checking a blockchain or anything like that. And I just want to stress, because I think this is kind of the mind-blowing part of Snarks, or one really mind-blowing thing about Snarks. They're tiny and easy to check, no matter how complicated the computation is. So you could run a computation for 1,000 years, and at the end, have it produce a Snark that said, the result of the 1,000-year computation is 42 or whatever. and you wouldn't have to rerun that computation yourself to know the results. So a baby that was born 1,000 years in the future, after the computation had finally finished, could check the baby who knows how to check SNARKs, can check the SNARK and know that the answer really is 42, even though they weren't around for that whole time. So it's kind of, I don't know, it's kind of crazy. All right, so yeah, someone wants some of that coffee. No, I don't blame you. Okay, so how are SNARKs used in Coda? Let's dig into it. Well, updating a blockchain, okay, that's just a computation. And as we said, SNARKs can certify any computation. So leads us to the clear conclusion, we can have processors produce SNARKs that they're updating the blockchain correctly, okay? So now, instead of end users checking the blockchain themselves, they can just check this little certificate that was produced by the processor that said, hey, yeah, I updated the blockchain, and now it's in this state. And remember, this certificate is tiny and easy to check. So the end user, they don't have to see the whole blockchain. They just have to see this little certificate, and they can check it super quickly. Okay, cool. So user is, you can essentially get a full node level of security while only having to download a few kilobytes and spend a few milliseconds computing. Let's try and really kind of see how in Coda exactly SNARKs are used. So we'll start with kind of a first attempt, which will not be what we end up with, which is to use one SNARK, one little certificate, to stand in for each block. Okay, so how it's going to work, as we said, the processor is going to produce the SNARK, this little proof that they're updating the database correctly, as they update it. So when they produce a block, they also produce this. Certificate that said, "Yeah, I really updated the database correctly." And let's see what it looks like. Okay, so here's the completed certificate. It's like many self-portraits, it's maybe a bit flattering, but nonetheless. And what the certificate basically says is, I know a block which, if you apply it to database 1, check all the transactions, move the money over, check the double spend, then the database will be in state 2. So you could say simply, I know a block, or you could say simply, you can get from database 1 to database 2. Okay? So the processor produces a certificate which basically says you can get from database 1 to database 2 by some block. It's a SNARK, so it's just a kilobyte or thereabouts, remember, which means no matter how big the block it was, no matter how many transactions were in it, if you want to be convinced that you can get from database 1 to database 2 with a block, all you need to do is get this little certificate and you're good to go. What does the kind of flow look like for the end user in this world? Well, first, they get the certificate that says you can get from database 1 to database 2. Then they get this Merkle path into database 2, which to see that their balance really is $17, for example. And if you're not familiar with Merkle trees or Merkle paths, you can think of a Merkle path as some kind of proof that really this is your balance in this database. As a result, you can know that your balance is what you think it is, $17, without actually having to see the block that moves you from database 1 to database 2. All you have to see is this little certificate. Okay, cool. But that kind of begs the question, like, what if you didn't know that database 1 was valid yet, right? So that's all well and good. If you already knew that database 1 was valid, this saves you from having to see the block that takes you from database 1 to database 2. But, I don't know that database 1 is valid yet. So what to do? Well, we can kind of notice that you can kind of chain these certificates. So if you have a certificate that says you can get from database 0 to database 1, and a certificate that says you can get from database 1 to database 2, taken together, I can kind of think of these as like a whole certificate themselves, which says you can get from database 0 to database 2, right? Because I know I can sort of glue them together, right? If I can get from 0 to 1 and 1 to 2, then I know I can get from 0 to 2. And it doesn't stop there, okay? Let's say we have another one that says you can get from database 2 to database 3, then I know I can get from 0 to 3. And if I have one that says you can get from 3 to 4 as well, I know I can get from 0 to 4. So in principle, you could think that you could use a sequence of SNARKs instead of a sequence of blocks if that sequence of SNARKs was smaller. So if each SNARK was smaller than each block, you could just send a SNARK around and have sort of a chain of SNARKs instead of a chain of blocks. And then the user could just sort of check, the end state of this one is the start state of this one, and they all connect up all the way from the genesis block all the way to the present moment. This is probably a win. I mean, blocks are already a lot larger than a few hundred bytes, less than a kilobyte, what a snark is. So that's probably a win, but it doesn't sort of solve the fundamental problem of linear growth. So the blockchain still grows linearly with the number of transactions that happen. OK, so that leads us to our second attempt, which is what Coda actually does, which is to use one snark to stand in for the whole blockchain. The main idea behind this is this really kind of amazing idea, which goes back to a 2008 paper of Valiant, I think TCC, which is recursive composition of proofs. So we can notice checking a snark. OK, well, checking a snark, that's itself a computation. And snarks can certify any computation. So we can certify the idea of checking a snark within a snark, which means we can kind of chain multiple snarks together to get one snark that stands in for all of them. And if that was confusing, we're gonna kind of dive into how exactly that works and step through it kind of step by step. OK, so let's recall. We had this proof before, the certificate that said you can get from database 0 to database 1. And we checked it, and it was correct. We ran the snark checker, and it said, yep, that's a good snark. And then we had this other one that said you can get from database 1 to database 2, and then we ran the snark checker, and it said, yep, that's a good snark. OK, well, that process of checking these two snarks, that was a computation, which means we can make one snark that stands in for the computation of checking those two snarks. And we get one mega snark, which is still just the same size, less than a kilobyte, which says you can get from database 0 to database 2. Because it basically says, hey, I ran the snark checker on some snark that got me from 0 to 1, and then I ran the snark checker on another snark that got me from 1 to 2. But taken together, that's really a certificate that you can get from 0 to 2. But the amazing thing is that because this is still a snark, it didn't get any bigger. It's still just less than a kilobyte. OK, so that's great. We can get from database 0 to database 2. And then let's say we did the same thing. We had these two proofs, one that said I can get from 2 to 3, and one said that I can get from 3 to 4. Well, again, we can stick those together into one that says I can get from 2 to 4. OK, and then we can just do this trick again. I check this snark, it says I can get from 0 to 2. I check this snark, it says I can get from 2 to 4. The process of checking those snarks is a computation, which means I can make a snark that stands in for that whole process. And thus, I can get one snark, still less than a kilobyte, which says I can get from 0 to 4. And you can see at the bottom here, it sort of has all these little snarks in some sense inside of it, but they're not really inside of it because the size doesn't grow. OK, awesome. So what does the life of an end user look like in this world? OK, so to begin with, they first just download this less than a kilobyte blockchain snark, which proves you can reach database 4 from the genesis state. Cool. Then they download this like 20-ish kilobyte Merkle path to get their exact account info, which says, you have $17. So now they learn, great, I have $17. And that's it. They're happy. So what they got is essentially a full node level of security, syncing from nothing, with only having to download a few kilobytes and a few milliseconds to check the snark. So that's kind of like a huge win in terms of decentralization, because it means users don't end up having to delegate trust to other participants in the network. And let me just say this is really interesting from the point of view of scalability. So most people, when they talk about scalability, what they're talking about is increasing throughput. So they say, we only do a few dozen transactions per second today. That's not realistic for like a real payment system. We want to have everyone sending transactions. We're going to need at least thousands of transactions per second. And they're definitely right. I mean, there's no arguing with the fact that to make a real decentralized peer-to-peer payment system, you need to be able to handle massive throughput. But increasing the throughput only makes this checking problem, this verification problem, harder. unless you have some mechanism for sort of mitigating the massive influx of data that comes with increased throughput, you're really just kind of throwing coal in the fire, so to speak. Just to be concrete, if you have a cryptocurrency that's doing like thousands of transactions per second, that results in like terabytes of data every week, which are needed for verification. And this is a kind of Red Queen's race. So if anyone's familiar with this little story from Alice in Wonderland, but basically for almost everyone in the system, the blockchain would be growing faster than they could possibly check it. So this is like a huge problem from the point of view of scalability. So that's about all I have today. Coda achieves this kind of cool property, which is sort of decentralized at scale. And please, here are some pointers to us on the web. I'm Izaak Meckler on Twitter. We're Coda Protocol, codaprotocol.com, and just a shout out for people who are interested in kind of getting their hands dirty with Snark programming. We have a pretty cool OCaml DSL called Snarky, which for programming Snarks that you can find on GitHub. And there's like talks on the web if you want to learn more.
Izaak, really clear, and you have this gift of being both a genius programmer as well as a good communicator at the same time, and that's rare in my experience. And the audience noticed that as well. So bravo, great job here. I think you clarified this for a lot of people here.
That's sweet of you to say.
I'm not just flattering you. You have a natural educational knack to teaching people concepts in a way that they can understand. I think the cartoony diagrams help too. So this is great, man. So I have a question for you, which is, okay, so let's say you've got a really powerful mining pool with tons and tons of hard drive space, right? Which is the majority of like the Bitcoin network and other networks. Does hard drive space even matter in those environments, given that they have such vast resources they can tap into?
Yeah, so I guess I should say, first of all, just to kind of like well, there's sort of two parts, I think, to answering that question. One is hard drive space is not the only resource. There's also bandwidth and compute for actually verifying things. But I think the more, what sort of gets to the heart of your question is, are we going to delegate trust to the miners or not, right? Like we kind of want to live in a world where the end user can actually have like oversight over the entire process of the computation that's like producing the data that they're interacting with. So if you're in a world where we're like, okay, maybe to actually check the system, we need like a super mega computer in a data center. What that's effectively doing is just saying we're willing to trust the miners who are like running these super mega computers, and basically giving up our ability to like have oversight over them. So if we want to kind of build a system where the end user can actually have insight into what is actually going on in the system, you need to have some real verification mechanism, which doesn't require enormous resources.
That makes a lot of sense. And are you guys? So you mentioned this is a cryptocurrency, and you're not building this necessarily as a smart contract platform or a scalable blockchain. Is that correct?
Well, I mean, I would say this is a scalable blockchain.
But for compute purposes,
it is.
I guess
it is. Okay. So, right. Okay. So, as I kind of alluded to, SNARKs are super versatile. They can certify any computation. It could be smart contracts or just payments. For the initial version of the protocol, we're focusing just on payments. But down the line, we're definitely going to be looking into adding the smart contract functionality. Because I think like it's sort of even a clearer win in that setting, because verifying for yourself becomes even more.
And so when you say you're going to initially start with payments, what does that look like? Is that a Ripple alternative, for example?
Oh, no. So I mean, I guess what I should say is you can think of it as analogous to any real cryptocurrency protocol. So any kind of decentralized peer-to-peer cash. So like Bitcoin, like well, maybe like Zcash without privacy. I mean,
and what do you think some use cases would be initially for that? Would it just be for kind of peer-to-peer payments? Is that what you're thinking?
Well, yeah. So that's kind of our initial our initial thing that we're focusing on. But I guess at a somewhat higher level, the real mission is to make it possible to build software that users can have oversight over, to make sure that they're sort of respecting the user. So right now, as a first step, even in cryptocurrency, which is like this, really there's like a demand for kind of this kind of trustless oversight. Even that domain is falling short, and so I guess we see like the establishment of like a really kind of trustlessly verifiable public state for money, for other things too, as kind of a first step in this like greater goal of building building
That's
software.
great. I
That
mean, I could see so many applications of this beyond cryptocurrency.
Yeah, I think there's a lot of cool ones. So like one that I kind of think about a lot. Really, whenever you're interacting with a software system, you really do want to have oversight over it. Like right now, we kind of we're sort of at the mercy of these opaque systems that we really have there's no transparency at all. And I think cryptocurrency runs the risk of that happening as well. But I wanted to give an example. Sorry, I almost forgot. One thing that's really cool is right now, like, okay, you receive an ad, let's say, that was generated by Google. You have no idea how that ad was generated. Did it use my race, my socioeconomic status, my gender to target me? Did it use my medical history? There's no way actually for you to know what kind of went into generating that ad. So one application that I think is really cool is a future where, for example, I don't like ads, but if we have to live in a world with ads, let them at least say this. Every time you get an ad, you also get like a little proof that says, hey, this ad is not targeted at you using sensitive personal information. So for example, things like that. And I think there's like a lot of other applications too in this kind of like user respecting software.
And do you think that you would
vein.
kind of build your own blockchain from scratch that does this beyond your cryptocurrency, or would you partner with some of the existing blockchains and augment them with these innovations? What do you think?
Oh, so yeah, okay, so we are building like a totally new blockchain. It really to kind of I would like to see this kind of thing on every blockchain. I mean, I think there's no reason, really you want users to be able to have this kind of oversight everywhere. Unfortunately, Snarks, let me say it like this, like if you want your protocol to be sort of snarkable, it's very important that you kind of keep that as a design constraint from the very beginning. So if you kind of just go ahead and design a cryptocurrency protocol the way people did, without this constraint in mind, picking your cryptographic primitives, with other constraints in mind, you're going to end up with something that verifying inside of a snark, that protocol is going to be basically intractable. So I guess I should say, like, for the foreseeable future, it would be kind of hard to transfer this.
Makes a lot of sense. Okay, we've got some questions from the audience here for you. And do you want to stop sharing your screen so we can see your face a little bit better? So the first question is, how are these certificates organized or downloaded and managed by the user or the user's wallet? How is it formatted? Are there files? Like, I guess what he's asking is, what is the persistence of these certificates with respect to the user's wallet? You still there? Oh, he might have jumped out there for a second. So I'll invite him back in just in case we lost him. But in the meantime, I polled the audience and asked them a question because I was curious about you. Is your mind blown by Izaak's presentation? And looks like we have an 8-to-1 ratio that the answer is yes. So the audience seems to be very interested in Coda and zkSNARKs. So let's see here. If we can get Izaak back here. Oh, Isaac's here. I'm going to invite you back on screen, Izaak. You just got your...
Oh, hey, sorry about that.
Just wait a second here for Izaak to reconnect. Here's Izaak.
Hey, sorry about that. I accidentally closed my video instead of the screen share.
Oh, no big deal, buddy. So anyway, we polled the audience, and like 21 people have their mind blown, and only 3 people do not have their mind blown right now, which is a good sign.
Okay, good. I'm glad.
So did you get the question about how are certificates organized and persisted within a user's wallet? Is the question.
Okay. So I guess kind of a way to think about this is the certificate is really just standing in for the whole blockchain. So instead of having to download a blockchain, which you usually do with a wallet, instead you just download this sort of blockchain certificate, which says there is a blockchain, which if you had seen it, would convince you that you had this much money. So there's really only one certificate that the user that the client has at any given time, which is kind of standing in for the whole blockchain. I hope that makes sense.
Makes sense. Next question is, what is the incentive for the miners to generate the zkSNARKs?
Okay, yeah, that's also a very interesting question. So the proof production and the block production mechanism are somewhat decoupled, but essentially there is the processor you can think is incentivized via transaction fees to produce proofs. And anyone on the network actually can contribute proofs for fees.
Great, thank you. Next question is, as far as I can see, zkSNARKs is already being investigated for this kind of application. What other stuff will differentiate Coda once, say, Ethereum incorporates SNARK tech? And I guess this kind of harkens back to the answer you gave earlier that you kind of need to be designed for SNARKs from the get-go. Right?
Yeah, so I think, yeah, I mean, that's essentially how I would think about that. It would be kind of hard to bordering on basically intractable to incorporate this kind of technology into like kind of an existing smart contracts and payments protocol.
Not only is it technically intractable, but it's probably politically intractable too, because you've got, how large is the Ethereum install base right now, and how powerful must that organization be to make a vote this drastic to change their protocol? I mean,
right. I mean,
even embracing like Casper and some of these other innovations is taking quite a while.
That seems like, yeah, I mean, that seems like a likely blocker to me as well.
Okay, how can we get involved and participate in the token issuance, and what is the development roadmap and timeline?
So there's no public plans on issuance yet, but please, check out our website to kind of stay up to date, sign up for our newsletter. In terms of development roadmap, right now we have a prototype that uses proof of work. We're currently in the process of doing some finishing touches on that and moving it over to use proof of stake as a consensus mechanism, and we hope to have a testnet ready in the coming months, next few months.
Thank you, great. Let's see, the next question you've already answered, which is compared to other blockchains and other blockchains adopting your tech. Next question, which is, as full nodes currently require processing and validating and storing the whole history of the chain, do you see a future where full nodes become a second tier, where transaction processing occurs, and the prime tier is where less of the frequent full chain validation and storage exists? For example, using zkSNARKs to summarize a significant amount of the chain's history, periodically allocating further history to a reference or prime tier and accepting new summarization in its place. Does that question make sense to you?
I think I roughly follow. So I guess I can answer that by saying, in Coda, no one has to store the transaction history. Some people, namely the transaction processors, stakers in Coda, have to store the current state, so the account balances. But the majority of users only need to download the SNARK that, as you said, summarizes the whole blockchain, the whole history. And actually, no one in the system has to store that history itself.
Great. And the last question from Duke is, how does consensus gathering enter into the chaining of SNARKs into replacement/recursive SNARKs? Where does the SNARK get its decentralized redundancy trust?
So if I kind of understand what the question was getting at, I think it was something like how do you check consensus inside of a SNARK? I guess I would say it like this: checking a blockchain. I didn't totally. I guess I didn't make this very explicit in my presentation. But if let me say it like this: the process of checking a blockchain, checking all the consensus requirements. For example, checking how long is this chain and so on. Is itself a computation, and there's sort of a final result of that computation, which is what is the ledger after checking all the accumulating all the transactions, and what is the strength of this chain? So what is the accumulated strength of this chain? And the snark is also checking that. So it's checking the proof of stake, and it's sort of updating the accumulated strength of the chain as you add more and more blocks in it. And that's actually summarized in the snark along with the current sort of account balances.
Great, thank you, Izaak. So great. So as for next steps for our audience, please check out the resources on the Coda website. The links were presented earlier in Izaak's presentation today. And Izaak, any parting words before we say goodbye for today?
No, it was really nice. Thank you for organizing, Ed. And yeah, check out our website, Twitter, etc.
Awesome. Very, very cool project. I think this is a huge inspiration for everyone in the audience about what can be done if you think out of the box and challenge some of the base assumptions about blockchain. So thank you, Izaak, and thank the rest of your team as well for helping out and being here in the chat. Guys, we'll be right back with Wei-Ting Liu, who's the founder of Code Mentor and the Dev Protocol, and he's here to talk about building developer communities and inspiring developers. So Izaak will be right back, and thanks again for your time, Izaak. You made a difference for the nonprofits today by being here with us. Take care.
Okay, thanks.